Okay, good evening and welcome. Why don't we go ahead and get started? I'm very pleased to see that we have a capacity audience on this rainy night, and I apologize in advance to people who are outside who may not be able to get in. We tried to set up a simulcast room, but I'm not sure we'll be able to do it in time. Okay, so welcome to this public lecture on this rainy night. It's a testament to Dr. Ramachandran that so many of you are here tonight. My name is Sam Wong, and I am chairman of the Committee on Public Lectures here at Princeton University, and I'm here to tell you mainly about the lecture series. Before I begin, I ask you to please set your pagers and cell phones to a setting that makes me unaware that you are carrying it. So if you could please do that, that would be wonderful. Okay? And I see you reaching for your phones. That's great. Thank you. If you'd like to learn more about the public lecture series, we've had a very good season, and we're going to have more good speakers coming up. These talks are simulcast on cable. They are also web archived, and so you can see them later on at your leisure. And we have many of these talks. We've been very lucky so far this season. Coming up in the near future, we have the pianist Alfred Brendel. We have the writer Javier Marias. We have coming up at some point former Prime Minister of Italy, Romano Prodi. Andrew Sullivan, the conservative commentator, or some people call him a conservative commentator. And John Waters coming in the spring. Tonight's lecture is in the Lewis Clark Van Uxem series, and this series is endowed by Lewis Clark Van Uxem from the class of 1879, and this series is dedicated to scientific lectures for the most part. And just to give you a sense of what kind of speakers we've had in the past speakers have included Edwin Hubble, James Conant, Carl Sagan, Jared Diamond, Lord Robert May, and neuroscientists in this series have included Michael Gazzaniga and Antonio Damasio. Okay, so that's just to give you a feeling for what kind of people we've had here in the past. And just last week, Sean Carroll, the developmental biologist. I should also say that in addition to being chair of this committee, I'm a neuroscientist, and I'm especially honored to have tonight's speaker tonight. As a neuroscientist and writer, I am full of admiration. Tonight, Professor Ramachandran will be introduced by Professor Jonathan Cohen, and Professor Cohen is Eugene Hillman Higgins. Professor Cohen is Eugene Higgins, Professor of Psychology and co-director of my institute, the Princeton Neuroscience Institute. Professor Cohen.
Would have been better to get my name wrong, I think, but that's okay. Thank you very much, Sam, for allowing me this honor to invite Professor Ramachandran back to Princeton and for having the opportunity to introduce him. I could keep it short and sweet and yet accurate by saying that Professor Ramachandran is a force of nature, not just within neuroscience, but I think on the sort of the social scene. He's what some of my colleagues refer to as a public intellectual, somebody that can actually take fundamental insights in complicated domains and translate those into terms that a broader audience can understand, and I expect that you will experience that tonight. But I wouldn't be doing due diligence if I didn't say something a little bit more nuanced and specific about his background. He is trained both as an MD and a PhD. He received his MD from the Stanley Medical College in Madras, India, and his PhD in neuroscience and psychology from Trinity College at the University of Cambridge. Then moved on to Oxford, where he did neurophysiological work with advisors the likes of Horace Barlow, Colin Blakemore, and Witterich. In 1983, he joined the faculty at the University of California, San Diego, where he has remained and is now the director of the Center for Brain and Cognition and also an adjunct professor of biology at the Salk Institute. He has obviously countless papers, nigh on 200 scientific publications, including many broader audience publications such as invited reviews to Scientific American. I think he has 5 of those. He's received numerous awards, obviously too many to go through here, though I thought I'd mention a couple. One was the Padma Bhushan, which I was just asking him about, that he received from the President of India, and my understanding is that it's roughly the equivalent of knighthood in India. And he's also been named as Newsweek as a member of the Century Club, one of the 100 most prominent people to watch in the next century. He has a remarkable web presence, not surprising. I think you'll agree after you've heard him speak. His laboratory has a website featuring various visual illusions that I know have drawn many into neuroscience in the first place. There are videos of his public lectures and television appearances, including on The Charlie Rose Show, one entitled The Aesthetic Universals and the Neurology of Art. BBC and PBS specials based on his research. And what I found most interesting that I just discovered last night was a thoughtful and I think touching obituary of Francis Crick that he titled The Astonishing Francis Crick, whom he considered a close colleague and friend, and I highly recommend. His topics of research, though they began at sort of the low level of neural recordings, have over the course of his career to date spanned a truly astonishing array of phenomena. And indeed, in his obituary for Crick, he writes, "The most important lesson I learned from him on research strategy was that it is better to tackle 10 fundamental problems and succeed in only one than to tackle 10 trivial ones and solve them all." And then he puts parenthetically, "So obvious when stated, yet so difficult to practice." And yet I think his career is a very clear testimonial to success in that effort. They've covered phenomena such as visual perception, which I mentioned already, mirror neurons, which are thought by many to be one of the seats of our social abilities, synesthesia, a phenomenon that I wasn't even aware of until I looked through his work called, and tell me if I pronounce this right, I'm still struggling to get it, apoptemnophilia. That is a early developmental disorder that causes people to reject a limb of their own, not want to have that limb, and in fact desire to have it amputated. A rather morbid but fascinating phenomenon that he was telling us about over dinner. At my request, I will add, he was he studied autism and then topics as broad as the neuroscience of art and the big question, consciousness. I think one of the things that most of us the work that he did that brought him to our attention is work on the use of mirrors to overcome phantom limb pain. And I suspect he'll say something about that tonight. I hope he will, and so I won't say anything more about it, but I think it's a really nice example of his ingenuity and cleverness, and yet the deep insight that his work provides. Some may quip that this work is all, excuse the pun, all smoke and mirrors. Mirrors, yes, smoke, no, and definitely not magic, unless you consider his clever use of simple experimental designs to arrive at deep insights into how the brain works as magic. In neuroscience, I think he's actually achieved the ultimate status reserved only for the select few in a given field, and that is recognition by a single name. So Michael in music is Michael Jackson, thank you. Hillary in politics, I don't have to say, right? In neuroscience, when you say Rama, everyone knows who you're talking about. But I think what I consider most impressive about his achievements, and this I've witnessed firsthand once before, and I look forward greatly to witnessing it again, is his ability to communicate and to take the complex and render it in understandable terms. The brain is arguably the most complex device in the known universe. It's made up of 100 billion neurons. Each of them connects with about 1,000 to 10,000 other neurons, making for on order 100 trillion connections. And if you calculate how many possible circuits there are in a brain made up of 100 trillion connections, which is what we're trying to understand, what are those circuits, right? There are more of those than there are stars in the universe. So in the face of this complexity, how are we going to possibly achieve an understanding? Well, I think Rama's work is an example of how we can pursue that. And so with no further ado, let me introduce you to Professor Ramachandran.
Thank you. Thanks. Well, I'd like to thank Dr. Cohen for that lovely introduction, and thank the whole Princeton faculty and students for inviting me to give this lecture here today. As Jonathan mentioned, the human brain is the most complexly organized form of matter known to us human beings, and he gave you some figures and numbers to illustrate this. I might add that somebody has calculated, I don't know exactly how, but someone figured out that the number of possible brain states, permutations and combinations of brain activity, exceeds the number of elementary particles in the known universe. So this gives you some idea of the staggering complexity of the brain. The question is, how do you study it? There are many different techniques, functional brain imaging, such as what Dr. Cohen has pioneered and many others, doing experimental psychology, treating the brain as a black box, studying it at the molecular level. And what I do mostly is I've studied perception in the past, but recently what we've been doing, well, not that recently, the last 10, 15 years, we've been looking at patients who've had injury in a very small part of the brain, what we call a lesion, or a genetic change in a small part of the brain, as you'll see, producing characteristic changes in behavior in their mind, often restricted to that behavior. In other words, they have one major deficit with other functions being preserved intact, and this gives you some confidence in saying that that part of the brain is somehow crucially involved in mediating that function. is the whole strategy of lesion function correlation. So you're going to see many examples of that. Now, one of my favorite examples is the so-called Capgras delusion. We know that there's a well-known phenomenon called prosopagnosia. There's an area in the inferotemporal cortex, also called fusiform gyrus, is part of that area, where you find cells sensitive to phases. In fact, Charlie Gross, who's sitting here, is one of the people, was the first person, in fact, to describe these cells. And it turns out when you have bilateral damage to the fusiform gyrus in both hemispheres, these patients lose the ability to recognize people's faces. They can no longer tell whether somebody's Joe, Charlie, or mother, or father, or whatever. Even when they look at the mirror, they can't recognize themselves in the mirror. Well, they'll say, oh, it must be me because it winks when I wink, but it could be anybody, you know. And that's well known and led to the idea that there are specialized regions in the brain for recognizing faces. But far less well known, far more rare, is a disease called Capgras syndrome, which refers to certain patients who are otherwise completely normal, intact, but they'll look at their mother and say, doctor, this woman looks exactly like my mother, but she's an imposter. And he'll keep insisting on this, and no amount of persuasion can make him change his mind about it. Now, why does he do this? I mean, he's perfectly mentally lucid and intact and intelligent, but he suddenly starts saying his mother is an imposter. And the standard Freudian view of this is that this chap, when he was a little baby, had a strong sexual attraction to his mother. This is the so-called Oedipus complex of Freud. Not that I believe it, but that was Freud's view. And then as the brain grows, the cortex develops and inhibits these latent sexual urges. Thank God, otherwise we'd all be sexually turned on by your mother. Then it comes a blow to the head, bang, damages the cortex, and then these repressed sexual urges come flaming to the surface, and suddenly, inexplicably, you find yourself sexually aroused by your mother. And you say, my God, if this is my mother, why am I sexually turned on? So this must be some other woman, not my mother. Some other woman pretending to be my mother. Now this is an ingenious theory, as indeed all Freudian theories are. But it doesn't work, because I've seen this syndrome where a patient has this imposter delusion about his pet poodle. He'll say, doctor, this looks just like Fifi, but it's not Fifi. You know. Now you try and interpret this in Freudian terms. I mean, you have to say, it's a latent bestiality in all humans or some such rubbish. You know. So we said maybe we can explain it in terms of the anatomy. It turns out, let's see if I have the slide here. Oops, nope. It turns out that the visual images go to the visual areas in the brain, of which there are a couple of dozen, almost 30 areas in the brain. After processing the visual information, the messages go to the fusiform gyrus, which, as I already told you, recognizes not only faces but other objects as well. So there's a taxonomy of visual objects and faces going on in the fusiform gyrus. And if that's damaged, you get face blindness. You can't recognize people's faces. I already told you about that. Now, our reasoning was maybe in these chaps the fusiform gyrus is intact, but connections from face detecting regions to the amygdala, which is in the front of the temporal lobes, are disconnected or disrupted. The amygdala is involved in detecting the salience of what you're looking at. Is it a dog? Is it a tiger or a lion I have to escape from? Is it my boss? Is it the dean? Or is it my mother, for that matter? Okay. So the amygdala is doing all of that, and then if you detect a lion or a tiger, the messages cascade down the hypothalamic nuclei, down the autonomic nervous system. Your heart starts pounding, pumping more blood. Blood pressure goes up, heart rate goes up, and you start sweating. Okay. So our idea was maybe what's going on. And by the way, Ellis and Young in England had a very similar idea, almost in parallel. Somewhat different, but similar. What we said was maybe in these people the fusiform gyrus is normal, amygdala is normal, but the message does not get from the face area to the emotional centers in the brain. So the patient can still recognize faces. He says, it looks like my mother, but the message doesn't get to emotions. So he says, if it's my mother, why am I not feeling any warm glow or terror as I would if I normally looked at my mother? Okay. So then he kicks into this delusion and says, this is not my mother, she's an imposter. Now it doesn't make any sense to us because our brains are intact, but it's the only rationalization that his brain can come up with, given this very peculiar disconnection between vision and emotion. Well, how do you test this? Well, what we did was hook him up to a galvanic skin response detecting machine, which is like a lie detecting machine, which detects changes in sweating or skin resistance on the palm, and that tells you how emotionally aroused you are by something. So if you take a normal person and show him chairs and shoes and tables, there's no galvanic skin response. But if you show him tigers and lions or a Chippendale pin-up, or show him, or indeed his mother, there's a huge big jolt in the galvanic skin response. You don't even have to be Jewish, you know, you get this big. Anybody here will get a big jolt in the GSR. Now we put the patient in front of the computer, tables and chairs, there's nothing. But even when you showed him his mother, there's no galvanic skin response in this patient, supporting our idea of disconnection between vision and emotion. Now since then there have been dozens of cases after we reported where we show the same disconnection between emotion and vision. So this we think is the correct explanation for the Capgras syndrome. Intriguingly, when our patient David, when his mother walked in, he says, "Who are you? You look just like my mother." Mother walks to the next room and after 10 minutes phones him. He says, "Mom, how are you? Where are you talking from? It's very nice to hear from you." So the delusion occurs only on the phone but not in person. Now why would that be? Well, it turns out there's a separate wire, putting it quite literally actually, going from the hearing centers in the brain in superior temporal gyrus down to the amygdala. That wire is not cut by the accident. So when you're listening to on the phone, the voice, he identifies the voice as his mother and the warm glow kicks in, but when he sees her in person, there's the disconnection and he says she's an imposter. So the reason I'm mentioning this is a lovely example of what we call cognitive neuroscience, where you're taking a completely bizarre, incomprehensible neuropsychiatric syndrome, where a person says, "My mother is an imposter," but on the phone he says, "Hello, Mom," okay? And then you reject the Freudian view and come up with a very simple explanation in terms of the known anatomy of the brain, and then do a simple experiment that takes a couple of hours and show that you're on the right track, okay? So the next question is, how are all these connections laid down? Are they specified by the genome, present in early infancy, or is it shaped by the environment? It's the so-called nature-nurture debate. And I don't take sides on this. What I'm going to do is, first half of the talk is going to be about phantom limbs, where I talk about the extraordinary plasticity or malleability of the nervous system. Second half is going to be about a phenomenon called synesthesia, which Dr. Cohen alluded to earlier, which I think is telling you a lot about genetically specified connections in the brain. So you're going to see examples of both. So first let's talk about phantom limbs. Now I became interested in these, what's the title? Okay, so that's the brain, okay. I became interested in this, seeing patients in the clinic when I used to be a medical student, and that's a whimsical artist depiction of phantom limbs, and everybody here knows what it is. You lose an arm or a leg, you continue to vividly feel the presence of that arm or leg. It's not rare. 97-98% of patients who lose an arm or a leg have a phantom limb. And about half of these have excruciating, intense phantom pain, which is occurring repeatedly, and in about a third of that half, occurring for life. They're stuck with it for life. Usually lasts for a few years and starts fading. Okay? So it's a very serious clinical problem. So what's going on in these patients? So inspired by some earlier animal experiment, I did a very simple experiment. So I had a patient with a phantom limb. His left arm was amputated above the elbow, right there. He'd been in a car accident crossing the Mexican border, and he had a vivid phantom left arm. So I had him sitting on the chair, blindfolded. So remember, this guy's lost his left arm, has a phantom left arm, he's blindfolded, sitting on the chair. I simply took a Q-tip and did a routine neurological exam, testing his touch sensations, and said, "Tell me when you feel anything and where you feel it." And he said, "Well, that's my forehead, that's my shoulder, that's my belly, ha, it tickles, that's my chest. Oh my God, you know, I feel that on my phantom thumb. How about that? That's my phantom index finger. That's my phantom pinky." And I found there's a complete map of the missing hand on the face. So that's showing you the thumb region, index finger, pinky, ball of the thumb. And you can come back after a week and remap these receptive fields. They're very precisely delineated digits on the face. Now why does this happen? Well, let's go back to the so-called Penfield map of the body surface and the surface of the brain. Every medical student, every psychology student learns this. It turns out if you go to the side of the brain, to the post-central gyrus, which is shown here, okay, so that's a coronal section through the brain, and that's the post-central gyrus. It's a vertical strip of cortex. There's a complete map of the surface of the body on that strip of cortex. So you can see all the body parts mapped there. It's a continuous map, but there's a peculiarity. The head is not where it should be. It's not, instead of being near the neck, it's dislocated and it's below the hand. So this gave us the clue. So what's going on in this patient, we thought, was normally the signals from the hand skin goes to the hand area, face skin goes to the face area, right? Now that you amputated the hand, the arm, there is no sensory input coming to the hand region of the cortex. So the sensory input from the face skin, which normally goes only to the face area, invades the vacated territory corresponding to the missing hand and activates that, so the brain is fooled into thinking, whatever is interpreting that signal higher up, is fooled into thinking that you're touching the phantom hand, right? And that's why you get this very beautiful, precisely organized map. Now it turns out there is a second map, you see, here above the stump. Now why would you get the second map? So there's again index finger, middle finger, pinky, all of the, sorry, that's the thumb there, index finger, one finger is missing, I don't know why. But anyway, that's the second map. Now why would there be two maps? Okay, again go back to the diagram. So that region has been deafferented, so sensory input from the arm to the cortex, hand cortex is gone. Now the input from the face skin, which normally goes to the face area, is invading from this side. The input to the upper arm skin is going to invade it from the other side and going to activate this hand area. That's why when you touch him here, he experiences it coming from the phantom hand. So you get two maps, one here and one here. Not only that, it's modality specific. If you put a Q-tip in hot water and put it on his face in the thumb region, he'll say his thumb is hot. You put it on his pinky, he'll say my pinky is hot, doctor. You take a vibrator, put it on his face, he'll say my thumb is vibrating. So not only has there been reorganization, it's not higgledy-piggledy, it's very precise and modality specific, okay? And in fact, on one occasion, when I put the Q-tip there, the water started dribbling down his face. And I was curious about this, and he said, oh, the water is dribbling down my phantom, and he traced the water dribbling down his phantom left arm. And for fun, I said, stick your phantom arm top, about point to the ceiling. And he did that, and I again repeated it, and he said, oh my God, the water is flowing uphill, defying the laws of gravity, okay? Now, by the way, when we first, one of the things we learn is, both in medicine and science, especially in medicine, is patients don't lie. I mean, usually when you think they're making something up, it means you're not smart enough to figure out what's going on, okay? Of course, sometimes they are making things up, but most of the time they're not, okay? So, when we first discovered this phantom limb thing with the face map, it was just one patient in the initial instance, but I was convinced it was a real phenomenon. But when we tested him a week later, it was the same thing. And why would somebody make up a bizarre story like that, right? But then one of the referees in science said, well, you know, it's only one patient. So my standard repartee for this is, supposing I bring a pig here to the podium, and I were to tell you, this pig can talk. And you say, oh, come on, you know. And I wave my wand and the pig starts talking. What would your reaction be? Would you say, well, that's just an N of 1, show me another pig? You would say, my God, right? I mean, but that's precisely the reaction of many of my colleagues in neurology when you first discover something. And of course, sometimes you get it wrong, but most of the time, when you do, this particular finding with the face remapping has been replicated by dozens of groups, and it's a valid, robust phenomenon. And in fact, to be absolutely certain, we even did brain imaging, which you have to do these days, otherwise they don't believe you. Okay? So this is the right hemisphere, left arm is intact. This is using MEG, magnetoencephalography. The left hand corresponds to the green spot. Left side of the face is the red spot, and that's supposed to be blue. It's the left upper arm. Now notice when you amputate the arm, the green is missing on the right arm is missing, green is missing. But the face area, face input, and the upper arm input have invaded the territory corresponding to the missing hand. So you can correlate perceptual phenomenological changes with anatomical changes, which is one of the goals of cognitive neuroscience. Okay. Now, just when we had thought we had exhausted the possibilities with phantom limbs, we were looking at some other phenomenon, which is when many patients with, by the way, I can go on and on. If you cut the trigeminal nerve, one of the things we predicted is if you cut the trigeminal nerve, you get deafferentation of the face. Face is anesthetized. You then predict if you touch the guy's hand, you should feel it in his face. Sure enough, when you do that, you do a trigeminal nerve block and you touch the hands and the fingers, there's a beautiful map of the face on the hand, right? So this suggests very strongly that we're on the right track. Now, why is it interesting? Because it shows there's a tremendous amount of malleability or plasticity of connections even in the adult brain. Now, as medical students, we were all taught that connections in the brain are laid down in early fetus or early infancy, and there's nothing you can do to change these connections in the adult brain. Hence the lack of recovery from neurological damage after stroke, for example, or degenerative brain disease. What we're saying is that's not true. In fact, there's a tremendous amount of plasticity. You're talking about 2 or 3 centimeters across the cortex of plasticity in a 3 or 4 week period. Now, the question is, can you tap into this clinically? That's a whole another question. Okay? Now, the other thing about phantom limb patients, one of the things we noticed is these patients, about half of them will say they can move their phantom. And this is undoubtedly because the front of the brain, which is sending motor commands, continues to send commands to the missing arm because it doesn't know it's missing. And a copy, like a CC in an email, is sent to the parietal lobe and the cerebellum, and that is monitored and experienced as movements of the phantom limb. Now, in about half the patients, what we found was the phantom is paralyzed. It sounds like an oxymoron. How can a phantom be paralyzed? The chap says, my arm is like this, doctor, and he'll show it to you with the other arm. So my arm is like this, it's fixed, doctor, or it's fixed like that, and it's clenched in a fist, and it's excruciatingly painful. In many of these cases, what I noticed was these patients actually had an intact arm that was paralyzed. The nerve was cut, as in a brachial plexus avulsion, and the arm was lying in a sling, painful and paralyzed for several months or a year or so. And then in a misguided attempt to get rid of the phantom pain, the arm was amputated, not the phantom pain, the pain in the intact arm, the arm was amputated. The guy is then stuck with a phantom arm in a phantom sling with phantom pain. Okay? So now how do you get rid of this pain? As I said, it's a very serious clinical problem. People have done, one idea was that the neuromas, the skin is innervated by the nerves that innervated the hand, now innervate the stump and form little clumps of scar tissue, painful scar tissue. The brain is fooled into thinking that the phantom hand is painful. So they're going to remove the neuromas. Sometimes it produces partial relief, but by and large it's ineffective. Or they would go and sometimes they do a second amputation, believe it or not. Now think about it, it's illogical. Why would that solve the problem? Okay? Or they would go there and they'd do a dorsal rhizotomy, cut the nerves going from the arm into the spinal cord. Or they do a chordotomy. Or they go to a thalamotomy. All of these procedures, none of which have been evaluated, clinical trials by the way, and are notoriously ineffective in treating phantom pain. So what we found was, so we said, well, this guy's claiming he's not able to move his arm, and if he can move his arm, then maybe the phantom pain will be relieved. So I said, first of all, why does the arm get immobilized? Well, because the arm had been immobilized and the brain was sending a command for it to move. Every time a command went to the arm saying move, it's getting feedback saying, nope, it's not moving. Move, no, move, no. And somehow this gets learned by the brain, and we called it learned paralysis, somewhere in the superior parietal lobule or some part of the brain concerned with body image. So the brain is then, when you amputate the arm, the brain is stuck with this image of a paralyzed arm. So out of just curiosity, I said, well, what if you make the arm move again, so that the phantom is now obeying the patient's command? Well, how do you do that? He doesn't have an arm. So we said, let's use virtual reality. So I called up my colleagues at Caltech, and they said, well, you can do this. You can create a virtual arm and do all that, but it'll cost you about $2 million. And it doesn't work very well anyway. This is in the early days, about 10, 15 years ago. So then that's when I came up with this very simple technique of just using a mirror. So all you do is you take and it costs $3. You put a mirror in a box, on a table inside a box, and then let's assume I'm the patient, my left arm is amputated and it's excruciating painful, and it's fixed in a position. I put my right arm on the right side of the box, look at the reflection of the right arm in the mirror, as shown in the diagram. Can everybody follow that? So the left arm, So the left arm is the phantom, okay? And you're putting the right arm here, seeing its reflection, and it looks like the phantom has been resurrected. Then you say, send motor commands symmetrically to both hands, like clapping or conducting an orchestra or waving goodbye, so that he gets the visual illusion that his command is being obeyed, right? So my first patient was a guy who lost his arm 10 years ago. He had a brachial plexus injury, paralyzed arm, excruciatingly painful. Arm was amputated, and a painful, immobilized phantom limb for the last 10 years. So he came to my office and I said, I want you to look inside this mirror. And he looked at it and he started chuckling and he said, well, that looks funny. I can see my arm. Of course, he's not stupid. He knew it was a reflection. Then I said, I want you to move both arms while looking in the mirror. He said, well, I can do that, but I cannot move my phantom. You know that. That's why I feel so much pain. Every morning I try to see if this awkward position can be shifted in some way. Often it adopts anatomically impossible positions like this, like it's touching its own back. And I wish I could move it, but I can't move it. I said, look, try it anyway. He looked inside and he started doing this. And he says, oh my God, you won't believe this. My phantom hand, it's moving for the first time in 10 years. Then I said, close your eyes. He closes his eyes and he says, oh, nope, it's stuck, it won't move. Open your eyes. Oh my God, it's moving again, it's moving again. And I said, does this make you happy? He said, oh, it's wonderful because when it's moving, the pain is relieved, the cramping sensation. Then I said, okay, well, this supports my idea of learned paralysis. And, but then I'm not going to get a prize for getting somebody to move his phantom limb. It's a completely useless ability, right? But then I said, well, maybe if he uses the mirror repeatedly, maybe he can get rid of the mirror and he'll learn to start moving the arm again, and then it'll relieve the pain. And secondly, I thought maybe there's a component of learned paralysis even in stroke, because in stroke, in the first few weeks, there's edema. As you know, what happens in a stroke is there's a clot that interrupts the fibers, destroys the fibers, going from the motor cortex down the brainstem to the spinal cord. And that's severed and there's no recovery, and that's why you have paralysis. There's very little recovery in the first few weeks. But maybe some of that paralysis is because the brain is swollen and there's a temporary interruption of signals through the white matter of the brain. So the arm doesn't move and the brain is stuck with this paralysis. So at least some component of the paralysis and stroke may be this learned component, which could in theory be affected by visual feedback. So we said, first thing we said was to ask this chap to take the box home, and I said, play with it for 1 hour a day practice, and then we'll telephone you. So 2 weeks later, he took the box home. I said, it's just $2, take it home, you know. And after 2 weeks, I phoned him and I said, how's it going, Derek? He said, it's great fun. I've been showing my girlfriend. When I put my arm in there, my phantom starts moving. It's never done that before and it feels good. But when I close my eyes or remove the box, it's rock solid. It won't move and it's painful again. And I said, well, you know, c'est la vie, you know. Then after 3 weeks, he phones me back and he says, Dr. Ramachandran, you're not going to believe this. I said, what? He said, it's gone. I said, what's gone? I was worried that his, you know, maybe I said, it's a box. Is the box gone? He said, no, not the box. He said, my phantom arm, which I've had for the last 10 years, has disappeared. And my first reaction was, I was extremely worried because about human subjects and ethics and all of that. Because, you know, you've changed somebody's body image permanently. And I said, does it bother you? He said, no, because on the contrary, you know, I have the excruciating pain in the wrist and the forearm and in the elbow. Well, now I don't have an arm. In the last 3 days, I have not had those pains. But my fingers are still, phantom fingers are still dangling from my shoulder. And the box doesn't reach. And they're still painful. So can you change the design or something? So get rid of it. Now, I was completely spooked out by this, but I'm convinced it was a real effect. And I always used to tell my medical colleagues, it's the first example of a successful amputation of a phantom limb. Okay. Now, that was about 10 years ago. Now, since that time, there have been several papers. The one recent one by Tsao and his colleagues in New England Journal of Medicine. And that was about, I don't know what the N is, it's about, I think it should be there somewhere. I think about 28 patients, about 1/3 of whom, about 10 patients were on the mirror, those patients. And look at the pain rating going from about 35-40%, which is kind of very painful, right? 70 being the most excruciating pain they've ever had, and then 0 being no pain at all. The pain drops in 4 weeks to 4, right? If you use a covered mirror, that means there is no mirror image, but you simply ask them to move it. The pain actually goes up, right? And if you ask them to do visual mental imagery on the phantom, they don't, neither the experimenter nor the patient knows which is the correct treatment. When you do imagery, again the pain goes up. Well, I'm sorry, no, wait a minute. Visualization, the pain goes down ever so slightly. Covered mirror goes up. The mirror goes down. Now you do a crossover, the ones who are in the controls also drop down to about 20%. So this is about as good as it gets in medicine. I mean, if you look at something like Prozac, it's a 5% change in depression, okay? So contrast this with all the other known treatments of phantom limb pain. They do very little, they help the patient very little. Okay, now let's talk about stroke. So we said, what about stroke? Maybe there's a component of learned paralysis. So Eric Altschuler is a postdoc in my lab, and I had 9 patients with stroke. This is about 11, 12 years ago. And we had patients with hemiparesis look in the mirror, put the arm, and do the same procedure, send commands to both hands. To our absolute amazement, about 3 of the patients showed substantial recovery of arm function. And I said, I'm not going to believe this, let's do another 50 patients. And Eric said, no, let's publish it. So I said, okay, you know. So we published it in The Lancet, which is a medical journal. And then after about 10 years, now there are about half a dozen studies, double-blind, 1 triple-blind controlled studies, showing dramatic recovery of function. Sorry, that's not stroke. Let me show you stroke. There, that's one example. Using the mirror, using various measures. That's hand movement control, showing recovery. And that's controls where there's no precious little recovery. Then you have another measure which is arm motor recovery. Anyway, it goes on and on like that. I can give you references later in the talk. Now, another thing I wanted to tell you about, so it works on stroke, not on all of them, but in a substantial minority. I would say in about a third of stroke patients is tremendous recovery of function, very striking recovery of function. In the paralyzed arm, using a mirror, to the point some of these patients for the first time can open locks on doors and start walking, for example, people who have never walked before, and all of that. And they've all been done with double-blind placebo controls. Okay, the other syndrome I wanted to tell you about before I get on to synesthesia is a condition called reflex sympathetic dystrophy, or RSD. This is not very widely known. In fact, most physicians don't know about it, but it's quite common. In fact, 5% of all stroke victims have this condition. Some estimate it's about 10%. And in other situations where you have a small metacarpal bone fracture, a tiny fracture in a hand bone, of course it's initially very painful, but as you heal, the pain goes away after a few weeks. But in some patients, the pain persists with a vengeance for weeks, for months, for years. The arm becomes swollen, inflamed, paralyzed. The entire arm gets involved from this tiny little injury. Okay? This is called RSD. And one theory of RSD is every time the patient tries to move his hand, he's getting intense pain. So the brain, there's a Hebbian link established between the attempt to move the arm and excruciating pain, and this gets formed into a form of learned pain. So I jokingly told somebody, I said, if you put a mirror, maybe you can treat learned pain. And this is sounding too hard to believe, right? So there's two groups who have now tried it, and that's the one group here. It's only about 3 months ago. So all you do is you get the patient with RSD, reflex sympathetic dystrophy, who has an immobilized, painful, paralyzed, inflamed arm, which has had for months, okay? Either after a stroke or after a trivial injury. And you put the mirror there, that's a mirror group going from movements in a visual analog scale, sorry, not movements, pain, from about 70% down to almost 5%, complete loss of pain in a period of about 4 weeks. And remember, these patients have had dozens of placebos on them. Everything that the physician does on them is a placebo, and none of it's just work. Again, you use mental imagery, the pain actually goes up, presumably because he's paying attention to the painful arm. Then a covered mirror, also the pain goes up, nothing happens. You cross them over, they drop down to 5% as well. So here is the first time as a cure for reflex sympathetic dystrophy, right? Okay, so now let's move on. I'll tell you, I thought we had exhausted phantom limbs, but there's two other, briefly I'll mention two other experiments which are quite exciting. One experiment is based on a recent discovery, well not that recent, about 10 years ago, by Rizzolatti and his colleagues. In fact, Charlie Gross was involved in some of these, anticipating in some of these studies. This involves what are called mirror neurons. So you record from the front of the brain, you find there are neurons which are called motor command neurons, which will fire when the monkey reaches and grabs a peanut. Another neuron will fire when the monkey grabs and pulls a lever. Another neuron when the monkey pushes something. Another neuron when he takes a peanut and puts it in its mouth. This has been known since the time of Vernon Mountcastle, I imagine, right? They're called motor command neurons. But what Rizzolatti and his co-workers found was a certain proportion of them, about 20 to 30% of these neurons, will fire not only when the monkey reaches and grabs something, grabs a peanut, but when the monkey watches another monkey reaches and grab a peanut. So these are called monkey see, monkey do neurons. It's as though the neuron, or strictly the network that the neuron is part of, is doing a computation that allows it to adopt an allocentric view. It says, this neuron is doing the same thing as I would be doing if I were to reach for a peanut. Therefore, that's what that monkey is about to do. So it's a mind-reading neuron. You could call it that, a theory of other minds neuron. Or I call it an empathy neuron. There are also mirror neurons for touch. Okay? So for example, if I touch you on your hand, there's a neuron in the somatosensory cortex, and especially in secondary somatosensory cortex, that fires. So there's a complete map of the body on your postcentral gyrus and just behind it. Okay? Now some of these neurons will fire if I watch you being touched. They're called mirror touch neurons, and I like to call them empathy neurons or Gandhi neurons. Okay? Because they're dissolving the barrier between you and another human being. The qualia barrier is being eliminated. Okay? And I'm being quite literal in saying this, because my question was, why is it then when the neuron is firing when you're watching somebody being touched? So my mirror neurons are firing, mirror touch neurons, when I'm watching you being touched. But I don't feel the touch when I watch you. I feel empathy, good for that, but I don't feel myself being touched. Why is that? Well, one possibility is I've got real skin here, which is informing those neurons. Don't worry, you're not being touched. You're just watching somebody being touched. So empathize by all means, but don't literally feel it, otherwise you'll get confused, right? And you can see, especially in the case of pain, and there are pain mirror neurons in the anterior cingulate, you empathize with somebody's pain, but you don't feel their pain, right? Unless you're Gandhi or Mother Teresa or somebody like that, okay? How do you test this? So I said there's a signal coming from your hand, vetoing or preventing the mirror neuron signal from reaching conscious experience and producing qualia. Well, all I do is I amputate my arm. So if I amputate my arm and I watch you being touched, I should feel it in my phantom limb, right? And amazingly, nobody had tried this because it's a crazy thing. I mean, why would you even ask a patient that? So I had two patients with phantom limbs who came to my office, and I said, I'm going to touch myself and hit myself, and I want to know what you feel in your phantom limb. And he said, okay. And I did this. He said, oh my God, you're tapping my phantom. And I said, do you feel the taps in your normal hand? He said, absolutely not. And I said, did you ever notice this before? He said, come to think of it occasionally, but I don't pay much attention to what's going on when somebody else is doing it and I'm doing it. But this is very clear, I feel it in my phantom. And there was a fairly topographically organized map on his phantom of me touching myself. I'm not touching any part of his body, right? And the interesting thing, by the way, is fairly accurate, but once I touch in one of these patients, I was touching my index finger repeatedly. He said he only felt it on his middle finger being stroked. And every time I tried the index finger, it was always the middle finger being stroked. Now, immediately you say, well, why the hell is that? Well, because this reorganization or disinhibition that's occurring is not very precise, right? So that's what you would expect, some slop in the system. Interesting thing is, this is precisely the sort of thing that we say is evidence against confabulation. If you were just trying to confabulate, why would you say it's the other finger that's being touched? But it's precisely the thing that the referee will say is evidence for confabulation. Is the evidence that I'm using to say it's not confabulation, right? But you try telling the referee that. Okay. So anyhow, we've done several patients on this, and most recently we did a brachial plexus block with my graduate student Laura. We did a brachial plexus block in a patient during surgery, so there's temporary anesthesia. And he watches another person being touched. He feels it in his, not phantom, in his real anesthetized hand. Showing that just temporary disinhibition, you can dissolve your consciousness in another human being. Remove this. So only barrier between you and me is the skin. Remove the skin receptors, I can feel your pain, right? By looking at you, of course. Okay. The other amazing observation is phantom limb, which may have, oh, by the way, this first patient I did this to went back home and phones me up the next day and he said, oh, you're not going to believe this. I said, what? I've been asking my wife to massage her own hand while watching her, and it helps my pain. Now, ordinarily I'd have dismissed this as rubbish, but having seen things with mirrors and stroke and all of that, I'm going to try it on a systematic basis and see if it's really true. But another observation of phantom limb is based on a discovery of Irvin Rock many years ago, who showed what's called visual capture. That is, if you take a lens, magnifying lens or a minifying lens, and put it in front of your hand looks much bigger, obviously. But Rock showed it also feels bigger. So there's a capture of somatosensory, tactile, proprioceptive sensation by the visual input. Clearly there's some sort of, what you're doing is combining information from different sensory systems, giving different weights of weighting to different sensory inputs, and then the combined perception depends on the relative weights. And in this case, vision gets a higher weight than proprioception. So I said, okay. So this guy comes to me with a phantom limb, and he says, doctor, my phantom limb is swollen and excruciatingly painful. And you sometimes hear this, and many of you have undergone dental surgery during dentistry, your face becomes swollen. And I don't know exactly why it happens. But this chap says the pain is, I've heard phantom limb patients say, my phantom arm is swollen, it's very painful. And I said, hey, why not put a minifying lens and shrink it? What happened then? I said, well, how do you do that? Well, put a mirror there, have him put his real arm there, so he sees a reflection of his real arm, so it looks like his phantom has come back, and put a minifying lens in front of his eye, so it looks like his phantom is shrunk. The guy looks astonished, and he says, my phantom is shrunk, it feels tiny, and the pain's gone, right? And we've done this now in about 3 patients with phantom limbs, and you don't need a swollen phantom, just a regular phantom limb. When the arm shrinks because of the visual capture, at a certain point of shrinkage, the pain disappears completely. And this could be clinically useful, and we're starting to do it properly on more patients. Now, at first you said, this is absurd, how can you shrink pain? Well, the visual capture can shrink proprioception, which is just another sensory input. Why can it not shrink pain? So it's not all that surprising if you really think about it. Okay? So anyway, we're done with phantom limbs. Let me move on and tell you about Galton and synesthesia. So we've talked about the malleability of the nervous system. Now let's switch gears and talk about genetic specification of connections. So Francis Galton, who was Charles Darwin's first cousin, noticed that some people in the population who are otherwise completely normal, a small tiny percentage, would claim that, would get their senses muddled up. They would claim that every number had a specific color. So 5 was red, 6 was blue, 7 was green, 8 was yellow, right? And sometimes tones, like F sharp is blue, C sharp is green, and so on and so forth, right? So why would this happen? Well, people thought they were just crazy. But since Galton's time, and Galton also noticed this runs in families and may have a genetic basis. Now, since that time, there have been dozens of case studies. Remember, this was 100 years ago. But mostly it was dismissed as a fringe phenomenon. People said, well, what do you make of somebody who says 5 is red? So one of the standard theories of synesthesia is they're just mad. They're just crazy. Now, that's not an explanation. I mean, maybe it's true, but that's not science, right? Now, the second possibility is that one theory is they're on drugs, like LSD and pot and things like that. And there may be some truth to this because it's much more common in Berkeley than at UCSD. Okay? But jokes aside, it is more common among drug users, and we can get to that later if you want. The third theory is that these people are just childhood memories. They've been playing with refrigerator magnets, and 5 was red, and 6 was blue, and 7 was green. And for some reason, they're stuck with these memories. Well, the question there is, why are we not all stuck with these memories, A? And B, why does it run in families? Right? You have to say the same magnets were passed down or something bullshit. So we said maybe the last theory is maybe they're just being metaphorical. And that is just as when you say cheese is sharp, cheddar cheese. So maybe they say F sharp is blue, right? So you say, well, cheese is sharp, that's just a metaphor. But why do you use a tactile gustatory adjective to describe a tactile metaphor to describe a gustatory sensation, cheese being sharp, right? So there's a circularity to that. And in general, you can't explain one mystery in science with another mystery. Saying, oh, synesthesia, that's just a metaphor, doesn't explain anything because we don't know what a metaphor is, right? So in fact, what I'm going to do in the remaining 20 minutes is to turn it around and say, synesthesia is a concrete sensory phenomenon. You can pin down its neural bases in the brain, and that in turn is going to lead you into understanding things like metaphor and creativity. So it's a long leap there. How are we going to do that? Well, the first thing we needed to show is they're not just crazy. And how do you show that? Well, we did a whole bunch of experiments, and some of these were done by Ed Hubbard, who was my grad student, now at Vanderbilt. David Brang, who's currently my grad student working on synesthesia. Some of you may have guessed this slide was made by David Brang. Okay. These are, by the way, these are various other people working on synesthesia. I'm not going to mention all their names, but okay. Now, we know it runs in families. So now, why does it happen? First thing we wanted to show is it real? Is it a genuine phenomenon? Now, we were lucky in stumbling on, first of all, finding it's very common. We found 1 in 100 people, 1 in 100 people have synesthesia. Maybe there's 3 or 4 of you here in the audience. We also then later found it was 1 in 50, and now people are claiming 1 in 30 people have synesthesia. So it's very common to see numbers as colored, right? That number color synesthesia and tone color synesthesia. So I said, how do we nail it down? We found that 2 students in our class had synesthesia. First of all, we just went to the class and I said, how many of you see numbers as colored? And nobody raised their hands. And he said, oh, forget this. Then when I went to my office, there were about 9 people lined up there. They're just afraid to admit it because people think they're crazy. And they just came out, and then they came to my lab, and then we started studying them. And 2 of them, they said it's extremely compelling, the colors, when they see the numbers. So we call these lower synesthetes, and we're lucky we stumbled on them because this phenomenon is only seen in these lower synesthetes. What is the phenomenon? What we did was, we did a Treisman experiment. Well, actually, Jake Beck, but related, right? So what we did was we showed these people an array. So 2 was red and 5 was green in these synesthetes. There's a whole bunch of 5s in the screen. Embedded in that, there's a bunch of 2s. And you can kind of hard to spot it. There's a 2 there, there's a 2 there, there's a 2 there. And normal people, non-synesthetes, take about, 10, 15, 20 seconds to name the shape, embedded shape. But a synesthete looks at it and he says, oh, it's a red inverted triangle. Because presumably, and he says it looks like a red triangle embedded in a forest of green trees. So he has the qualia, and if you measure it, you can measure that the reaction time is 1/3 the reaction time as when you have a normal person see it. So this suggests it's a real phenomenon, because if he's crazy, how come he's better at it than us? Right? And we showed this in 2 of our subjects. Now we then ran into higher synesthetes who don't show this phenomenon, but I'll get to that later. Now, then other thing in these 2 patients is contrast sensitive. You take the number, and instead of black on white, you make it gray on white, and the color saturation drops until it gets very low saturation. You still see the number 5, but there is no color, right? So if it's a high-level cognitive phenomenon, how come the color disappears at low contrast in some synesthetes? Now the other thing I want to tell you is that, okay, so far so good. This is all evidence pointing to the fact that it's a low-level perceptual phenomenon, it's authentic, they're not crazy and all of that. A number of other experiments I could mention, but I won't go into it. Well, let me mention it anyway. Now, that's made up of 2s and 5s, and believe it or not, it's 2 frames of a movie alternating, and there's a bunch of 2s and maybe a bunch of 5s, I can't even tell, forming a horizontal row going down. And, oops, I spoiled it. Okay, so there's and you cannot see any direction of motion, they're just twinkling. But you show this to a synesthete, this is what he sees. He says, I see a horizontal bar moving up and down. And he sees it well about chance, and I've never met any normal person perform just barely about chance. So this shows again he's not crazy, right? So, and it also shows this is a genuine sensory phenomenon because the color can drive apparent motion, at least in the 2 synesthetes whom we studied. Okay, now let's switch gears and talk about where it's going on in the brain. Well, we were struck by the fact that if you look at a cross-section through the fusiform gyrus, which is on the sides of the brain, in the temporal lobes, you find that in the fusiform gyrus there is Semir-Zeki's color area shown by a green patch, where cells respond to colors. So you can think of it as a color area in the brain. When it's damaged, you get achromatopsia, you get color blindness, cortical color blindness, caused by damage to the cortex rather than absence of pigments in the eye, right, which is a much more common type. But right next to it, Ed Hubbard and I noticed, was the so-called grapheme area, or number area of the brain, also in the fusiform gyrus, very close to it. So we said, what is the likelihood that the most common type of synesthesia is number color, and number and color represented both in the fusiform right next to each other. We said this is highly unlikely to be a coincidence. Maybe in these people there is some sloppy wiring, cross-wiring between these 2 areas. Now why would that be? So that every time you show them a number, there's a corresponding cross-activation of a specific color, so you get number color synesthesia. So it's a bit like the phantom limb, hand, face remapping. But in the case of the phantom limbs, there's been an amputation. Why would there be cross-wiring between these 2 regions in synesthetes? Well, the clue comes from the fact that it runs in families. There's a genetic basis. If that's true, so our hypothesis was that maybe in the infant brain, the fetal brain, everything is connected to everything, putting it crudely. And then the way you develop the classical modular architecture of the adult brain is by pruning the excess connections. So this pruning gene or genes may be defective in synesthetes. So there's defective pruning between these 2 adjacent regions, the number region and the color region, in the fusiform. So if this gene is expressed locally, just in the fusiform, right, because of transcription factors or whatever, then you get number color synesthesia. So far so good. We did brain imaging on this using FMR. I won't go into details. In a normal person, if you show a number, only that lights up. If you show a colored number rather than black and white, that and that lights up. If you show a synesthete, black and white number, both that and that light up. This is done with Ed Hubbard and Jeff Boynton at the Salk. And so that was published a few years ago in Neuron. Now since then, people have shown, Rolf and his collaborators in Germany have shown by DT imaging, there's actual increase in white matter between the number and color area within the fusiform. It's about as good as it gets. You can make a prediction based on psychophysics, say what part of the brain is involved, do brain imaging, and even do DT imaging and showing that there's more wires. Okay. Now so far so good. Now, out of curiosity, I said these people see numbers as colored. Okay, this has been known for 100 years. I said, well, what if you show them Roman numbers, like V or V1, instead of Arabic 5 or I should say Indian, they came from India. Indian 5 or Indian 6, okay? So what would happen then? So we had these 2 synesthetes, we showed them Roman numbers, and they said, well, it's obviously a 5, but there's no color. I mean, I know it's a 5, but it's not a color. Now that's important because it's showing that it's not the abstract idea of number or numerosity or ordinality or cardinality, any of those abstract ideas, but it's a visual shape, the grapheme, that's producing the color, which fits our theory that it's happening early within the fusiform, because the fusiform is not telling you numerical concept. But then we found synesthetes, whom I call higher synesthetes, where it gets murky or more interesting, depending on your point of view. And these higher synesthetes will say, doctor, or not doctor, sir, professor, days of the week are colored. Monday is red, Tuesday is green, Friday is yellow, Thursday is chartreuse. Months of the year are colored. December is yellow, February is green, March is purple, and things like that. No wonder people thought they were crazy. What do you mean March is purple? Right? But remember my golden rule, if somebody sounds crazy, usually means you're not smart enough to figure it out. Okay? What do days of the week, months of the year, and numbers have in common? Obviously, sequentiality, numerosity, ordinality, this idea of sequence. Where is that represented in the brain? I don't know. Maybe Jonathan here knows. But being trained in neurology, I would say it's somewhere in the vicinity of the angular gyrus, because when that's damaged, you get the dyscalculius. You can't add 17 and you can't subtract 3 from 17. Although he can talk fine, he can play chess, everything else is fine, right? So a hunch is somewhere in that region is your number line and your representation of sequence and all of that. And there are higher order color areas, roughly in the TPO junction region. So if the cross wiring occurs there, you get a higher synesthete. And even calendars and days of the week are represented sequentially in this funny way. Then you get higher synesthetes. Now what if the gene is expressed throughout the brain so that there's cross connectivity everywhere? What would happen then? Well, remember I said, maybe I didn't tell you this, an odd thing about synesthesia, which has been known for about 50 years, is synesthesia, and has been confirmed by Ed Hubbard and a couple of others, is synesthesia is about 8 times more common among artists, poets, and novelists than in the general population. Now you say, why would that be? And one standard critical remark is, well, they're all crazy. Right? But again, that's not an explanation. What do artists, poets, and novelists have in common? They're all good at making links and metaphor. So you say, it is the east and Juliet is the sun. You don't say Juliet is the sun. Does that mean she's a glowing ball of fire? Now, oddly enough, schizophrenics do that. And this may have something to do with brain connectivity, but I won't go into that. It's another lecture, okay? But normal people say, well, no, it means she's radiant like the sun. She's nurturing like the sun. She's warm like the sun. You make all the right links. And of course, Shakespeare was a master at this. So, where am I headed with this? Okay, so in these people, the synesthesia gene, the cross-connectivity gene, pruning gene, mutated pruning gene, is expressed throughout the brain. And if you assume that concepts are also represented in different parts of the brain, there's greater propensity to link seemingly unrelated ideas. Hence the greater propensity to metaphor, hence artistic and poetic ability. So that's why synesthesia is 8 times more common among artists, poets, and novelists. This is, of course, pure speculation. But I suggest that this is why the gene persisted. Because why would this gene, which is completely useless and make you see 5s as reds, be present in 1 out of 20 people in the population? And natural selection would have eliminated it hundreds of thousands of years ago. The gene is useless. The reason it persists, I maintain, is because there's a hidden agenda. It makes certain outliers in the population more creative, more artistic. And whenever I say this, people say, well, why isn't everybody a synesthete if it's that good for you? If he makes it artistic and creative. Well, that's a stupid question, because first of all, evolution takes time. So maybe 100,000 years from now, we'll all be synesthete. Secondly, you don't want everybody to be poetic and artistic and metaphorical. I mean, some neurosurgeon is doing surgery on your brain, you don't want him getting metaphorical on you. So some degree of heterogeneity is fine. Actually, that smacks of group selection, so I'm just saying that it's not entirely a logically watertight argument, as you would have noticed. Okay, so anyway, so now what have we done here? We have started with, let me see what the next slide is. Okay, next we got interested in another completely unrelated phenomenon. I wanted to tell you about top-down influences in synesthesia, but I'm going to skip that. Oh yeah, I want to tell you about something really weird. We've now come across 2 synesthetes. The first one we saw was in UCSD about 10 years ago, and we actually had a paragraph on this in our original synesthesia paper in the Royal Society. So this paper mentioned a patient who would see, he came to us in our lab and he said, you know, I have a weird form of synesthesia. And I said, what is that? He said, I'm partially colorblind, and at the same time, but in numbers, when I look at numbers, I see colors which I cannot see in the real world. And he charmingly referred to them as Martian colors. And I said, it doesn't make any sense. And then suddenly it hit me. I said, it makes perfect sense in terms of our theory, because what's going on in this Martian color phenomenon, going back to the brain slide, is that maybe what's gone on in this patient is, he's a synesthete, so there is cross-wiring between number and color in his brain, but he's deficient in color pigments in his eye. So his peripheral vision, he cannot process color information, so he's partially colorblind. But if he sees a number goes to the grapheme area and then cross-activates the color node. So he's able to internally see colors which he cannot see in the real world, because you're producing color phosphines using numbers to shortcut the process. So we said that's about as good as it gets as evidence for the fact that synesthesia is a low-level phenomenon, not some high-level conceptual phenomenon, because how could how can you see colors that you've never seen before in your life in the real world, right? Now, we then came across a second patient who actually I saw in Boston last week. No, 3 days ago when I gave a lecture at Harvard. This guy comes to me and says, I see colors which I don't see in the real world in numbers, and I'm partially colorblind. Okay, so we're going to study them systematically, but I thought that was kind of fun. Okay, now, so what else about synesthesia? I'm going to close in a few seconds here, a few minutes. Okay, the other thing, evidence for synesthesia being low level is many of the synesthetes will report that any given number, too, will have portions that are blue and portions that are red. Okay, in some synesthetes. And this automatically suggests a hardware explanation rather than a software. If it's some conceptual number to color link, why would half the 8 be red, half the 8 be green? And here I think what is going on is some form primitives within the fusiform are being linked to colors rather than holistic graphemes. Now why that would be, I don't know. Okay, but again, it supports a low-level interpretation. Oh yes, last part about synesthesia. Okay. So this is another phenomenon observed by Galton, who's a very, very astute observer, is some people who don't have to be synesthetes, but he called them number form people. These people, when they ask them to imagine a number, all of you here, when I say imagine 1 to 10, visualize 1 to 10, roughly it goes from left to right. It's called a number line. We all have this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's very vague. You don't literally see the numbers that are out there in space. But these subjects, again quite common, 1 in 50 or 1 in 40, will say, I see 1 here, 2 here, 3 here, 4 here, 5 here, 6 here, 7, 8, 9, 10, 12, 13, 14, 15. It's an elaborate convoluted line. You bring them back after a month, as shown by Saitovic, bring them back after a month or 2 months, they'll draw exactly the same line with the same spacing between the numbers. So it seems like it's a genuine, authentic phenomenon, although nobody had proved it because they could have memorized it or something like that. So what we did, this is Dave Brang and I think others have done this too, but I only remember that we did it. Let's go to the number. Okay, that's an example of a number form. That's another example from our lab. So we just did a Stroop interference task. So you plot this guy's number line, bring him back after a week, and show him number 9 where number 12 should be, or number 8 where number 9 should be. And he's much slower at reporting the number than if you present it congruently. This is hard to fake, so you see you're on the right track, so there may be a basis to this. The other experiment we did is a bit more complicated for this audience. I won't describe it. But it's basically showing that number distance effect depends on geometric distance, not on numerical distance, but we won't go into that, okay? So anyway, number lines are real. The question is, why does it happen? Why would you get these convoluted lines in your head? Doesn't make any sense. Then I thought about it, and you see, our brain's number systems evolved very recently, maybe 10,000 years. Before that, we didn't have any numbers. I mean, we had a crude concept of number, but we didn't have a list of numbers like we do. You can't use a lookup table. There isn't one in the brain. You can't suddenly evolve a machine for numbers, doing numbers. So what you do is, very conveniently, you say, I'm going to map numbers onto space, right? And you've got a space, so representation of space is throughout the brain, goes back to Devonian times. Fish and lampreys of representations of space is very robust in the human brain. So you say, I'm going to map numbers onto space as on a graph paper. That's what I'm going to do. Now, if this mapping gets messed up, I'm claiming you get this convoluted number lines, this one-to-one mapping. So there's a shamelessly phrenological theory of Galton's number lines, but nobody else has come up with a better explanation. So I think it's the right one. But conceivably you could do brain imaging experiments to see if this is the case. Okay, so now the other phenomenon I wanted to tell you about, which will take me 5 minutes, is that okay? Yeah? Okay. I'm sorry? Yes. All right. Now we're talking about synesthesia, which involves pathological mingling of signals, and I said there may be hidden agenda and creativity and all that. Now that got me interested in just intermodality interactions, even in normal people. Things like the McGurk effect, ventriloquism, and visual capture, things like that. And then I came across an old Gestalt phenomenon, which has many different names, Maluma, Takiti, or I'll tell you about Buba, Kiki, okay? So let's take that example. Now let's assume these are Martian alphabet, just like you've got English alphabet, A is A, B is B, each shape has a corresponding sound, okay? This is Martian, one of them is Kiki, the other is Buba. So which one is Kiki? How many of you think the left one is Kiki, right one is Buba? Raise your hands. One or two mutants there, but how many of you think this is Buba and this is Kiki? Okay, all of you here. None of you is Martian, right? And so why the hell would you say that's Kiki and that's Buba? Well, it's because the sharp inflection of the shape, the visual shape, mimics the sharp inflection of the sound, Kiki, not to mention the inflection of the tongue on the palate, ki. And I think, by the way, I think this explains the emergence of proto-words and proto-language, a non-Sagerian view of emergence of proto-language, which I won't go into because it's another lecture, okay? But where is this illusion occurring? So the brain is extracting the common denominator between the visual shape and the sound and the tongue inflection in some, if you want to be mathematical, in some abstract Fourier space. There are high spatial frequencies here, here, and in the sound ki, and the brain is extracting that. Now this is not trivial, it's not just an amusing demo, it's absolutely fundamental, because it's telling you about something we call abstraction, which we humans are especially good at. Because this thing here is just a bunch of photons hitting your eye in parallel. The sound ki is a bunch of hair cells excited sequentially. They have absolutely nothing in common, right? But the brain is instantly extracting the common denominator of kikiness, that abstract property of high spatial frequencies, and saying I'm abstracting this property. And remember I told you about metaphors, that also involves abstraction, right? If you say Juliet and the sun, each word has a penumbra of associations, right? And any given word carries a penumbra of associations. In synesthetes, I claimed there are bigger penumbras of associations because they access cross connections. Hence the greater propensity to metaphor. So what's it got to do with this? Okay, I'm getting there. So let's get a Buba Kiki. Now where is this going on in the brain? So on a hunch I said, well maybe it's in the vicinity of the TPO junction and near the angular gyrus, where all the sensory information comes together in the brain. Okay, so that region there, you find that it's at the crossroads between touch, vision, and hearing. So it's an idea strategically located to combine information and to abstract information from individual sense modalities. So what happens when that's damaged? You get a condition called Gersmann syndrome, left-right confusion, dyscalculia, finger agnosia. All of this constitutes the Gersmann syndrome. And I said, what would they do with the Buba Kiki illusion? And we have a whole bunch of these pairs. We give them and they're just slightly about chance. They're terrible at Buba Kiki. But then the critical experiment was, what about metaphor? So what we said was, would these people be good at metaphor? So we gave them a whole bunch of metaphors like, all that glitters is not gold. And you tell most people, all that glitters is not gold, what does that mean? They'll tell you, well, it means that don't go by surface appearance. But these people will say, for example, not long ago I saw a patient in India, he said, well, if it's glitters that means shiny, it doesn't mean it's gold, it could be copper. Or it could be some alloy of copper. And you'd have to measure its specific gravity to be sure. So he's not stupid. He can, but the metaphorical meaning eludes him completely. And I said, does it have any deeper meaning? And he said, yes, of course. It means you'd be very careful when you go to a jewelry shop, especially here in India. So now the thing is, oddly enough, and I ought to mention this, I found 1 in 20 or 30 normal people have metaphor blindness. And I was very surprised by this. So you have to be careful in this business to make sure you have enough normals, right? So I've had normal people who say quite that. They only get the literal meanings of proverbs and metaphors, except after you teach them, then they start getting it. It's like some people don't have a sense of humor. They'll say they understand it, but they don't get it, right? So they have metaphor blindness. So we suggested that this region originally evolved for cross-modal abstraction, for abstracting across sensory modalities like Buba and Kiki. And then it became exapted for more high-level types of abstraction like linguistic metaphors. Now this is again pure conjecture, but it's supported by the clinical evidence that when that's damaged, you become metaphor blind, in addition to having difficulty with the intramodal interactions. Lastly, why did this region evolve and what is it doing? Why do you need a region for metaphor or doing Buba Kiki? First observation, the answer often lies in anatomy. First thing I want to tell you is, not only does it lie at the crossroads between vision, touch, and hearing, this structure, the inferior parietal lobule here, is small in lower mammals, slightly bigger in monkeys, big in apes, but enormous in human beings. So there's an explosive development of the inferior parietal lobule, especially in the human brain. Now, when you see that, you know, if you're doing evolutionary biology, there's something interesting going on there, something that makes human beings special. And I claim it's critically involved in many types of abstraction, right? Now, why would it evolve that ability? And you wouldn't have evolved the ability for metaphor out of the blue. I think it's because you were climbing trees and you have to match photons with a vertical, like a vertical branch, with a complex remapping to grab the branch. With the oblique branch, you have to obliquely match it. And again, these maps have nothing in common except the property of being oblique or vertical. So that's why you evolve this ability in the inferior parietal lobule. And in fact, in humans, this lobule split into two. Again, into the angular gyrus and supramarginal gyrus. The supramarginal being involved in skilled actions, rich in mirror neurons. and the angular gyrus being involved in the other types of abstraction I was telling you about, like numerosity, number, left-right confusion, metaphor, and things of that nature. So anyway, that's the most speculative part of the talk. I'll conclude by saying that when I got into this business, maybe 10, 20, 30 years ago, I was told there are certain questions you stay away from, like how does math represented in the brain? How do you fall in love? What is consciousness? What is synesthesia, right? Or what is body image? Or what is poetry? What is metaphor? If you did that, you won't get tenure, right? But now with all our great imaging tools, and if you do the right experiments on the right patient populations, you can actually, take synesthesia, right? Now that you've done all these experiments, you can start with a gene. There are people now trying to clone the gene in large families, right? You can clone the synesthesia gene. You can go from the gene to psychophysics. You can do the pop-out experiments, the contrast experiments. You can even find colorblind synesthetes. You can go to the anatomy by doing brain imaging, doing DT imaging, FMR. From that, you can go to metaphor, Shakespeare, creativity. So you've gone from the gene all the way to Shakespeare. You can do it all in one preparation, this quirky little phenomenon called synesthesia. So questions that until today have been the province of philosophers, like what is a metaphor, so on and so forth, we scientists can start studying. That's it. Thank you.
Questions?
Yes, I'm sorry I ran over it.
No, there's one for it. Perfect. We wait a long time to listen.
Okay, so I've been asked to answer questions, so we have about 10 or 15 or whatever.
I realize we're a little bit behind our usual time, so if people want to leave, maybe sneak out. There are two people with microphones. When you ask a question, try to have the microphone in your hand because we're archiving and cable casting. You're going to have to watch the microphones.
Okay.
If there is a cortical resection in an individual with a phantom limb, will that permanently eliminate the phantom limb, or will the brain change its map and send the impulse to another area?
You're saying that reorganization that has occurred, is that permanent? Well, so long as the arm is missing, it's permanent. Now, what would happen if you constantly stimulate the nerves or do something? Whether it'll again reorganize itself, I don't know the answer. I suspect it will. But you can't do that experiment on phantom limb patients because they've lost the arm. There's no way of restoring that input again. They've lost their arm for good, and the remapping persists.
Yeah. I have one other question. You described synesthesia as a lower level function rather than a higher level function. But I've read of individuals, particularly mathematicians, who are able, by means of colors, to perform higher mathematical problems.
That's a very good question. Well, it turns out that many mathematicians claim that they use spatial representation of numbers to do their computations. And it's not completely in an abstract mathematical space. So that kind of fits with what I'm saying, that the brain maps these abstract ideas onto space. And these people, for some reason, one of the things we found is that people with convoluted number lines, they'll say where there's a glitch in the number line, where there's a sharp bend, they have difficulty with arithmetic. So if you tell them subtract 17 from 4 and they're right next to each other, they get confused. So this shows that this really affects their computational abilities, these number lines. Now whether it enhances it in some people like Einstein, I don't know. It's a good question. And I suspect it does, but we have to measure it and show that it does.
Hi there.
Yes.
Have you ever tried inducing synesthesia by, taking advantage of the gigantic plasticity of the brain and creating an association between color and numerals?
It's a good question. Can you create synesthesia? If my theory is right, or our theory is right, that there's a genetic propensity to link things in early childhood, and that's why they've done these links, then you should not be able to take any adult and create synesthesia in him, right? And people have tried this with random shape, taking random alphabets with random colors and seeing if you can create synesthesia in normal adults. And the short answer is no. Maybe there's some controversy, but most people cannot get this result, even after hundreds and hundreds of trials. But of course, these people have had it for thousands of trials, so there's no strict way to answer that question. But a student of mine, Laura Case, is doing experiments, and David Brand, where he takes synesthetes who already have a propensity towards linking colors and numbers, whether you can teach them new nonsense graphemes with colors, and then convert them and create new types of synesthesia in these people, which they don't have before. So that might work and is related to your question. We haven't done that experiment yet.
Yeah, hi here. I'm glad you concluded with saying that you should always ask questions, because my friends are trying to dissuade me from not asking this. But I'm extremely curious if the phantom phenomena also occurs in the reverse, and not only in pain but in phantom pleasure, say if a patient loses a sexual organ.
Well, I mean, this is common knowledge that masochists and people like that, I don't know much about it, that you get pain and pleasure getting reversed. You know about that masochists in Cambridge who loved to take ice-cold showers at 6 a.m. in the morning and therefore didn't. Maybe there's some cross-wiring there, I don't know. Sure.
Let's go. So has the ability to make abstract connections and metaphors in people with, who are more creative come at the expense of other ability?
Does it extend into other...
No, does it come at the expense of other
abilities?
abilities?
The expense. Don't know. I mean, whether the hyperconnectivity makes them more creative, but maybe it makes them less rational, I don't know. It's a good question. But that's the advantage with this system. It allows you to address questions of that nature using DT imaging, using FMR, using just psychophysics, cognitive psychology, which are difficult to answer those questions. But synesthesia provides an opportunity to address some of those questions.
It's ready to go.
Hi. I'm sorry, I heard a lot of your lecture through the door, so you may have answered this before I got in. It was a little muddled out there. One of the things that I was curious about in phantom limb pain, I was very struck. I came into the part where you said the visual aspect helped a great deal. But has it ever been thought about, I mean, it must have been that by thinking the limb opening, even if it wasn't there, why wouldn't it have any effect?
It has no effect at all. In fact, they get insulted if you tell them that. But they say they try to do it all the time to see if it will relieve the pain. It doesn't work. In fact, those graphs I showed you from Tsao's group and other groups, that was a control, asking them to think and visualize and will the opening of the hand. And if anything, in one of the studies, the pain went up when they tried to will it to open. So the short answer to your question is no, it doesn't work like the mirror.
Okay. The way that we experience color and even metaphor, in my opinion, is very culturally based. And I was wondering if you have patients from several different cultures or more Western or...
Right. And one thing to remember is obviously 5s and 6, the graphemes are culturally, I mean, they're learned. It's not the specific shapes that are hardwired, but the propensity to link arbitrary shapes with color, that propensity is enhanced in these people. So when they start learning numbers. Now, with regard to whether there are cultural influences, that's inevitable, there might be, but we haven't studied that. But this phenomenon, to me, is a robust genetic phenomenon that lends itself to this kind of analysis. Whether there are other cultural influences remains to be seen. Yeah.
Hi. I was wondering if, I don't know if you addressed this, but when you represent the number in a color, for example, you actually write the number in red, can these people with synesthesia discern between which one is the real color and which one is their perceived color?
I didn't hear the last bit, so...
Can they discern between what is the real color?
Oh, I see. Yeah, they can. They'll say that I can see the color on the letter. I know it's actually black, but it looks red and it's on the black. They say it's ineffable. They can't communicate it to you because it's like you telling a colorblind person what red is. They have a peculiar subjective qualia, but they say, I know clearly it's a 5, but it looks red to me. Now, the higher synesthetes will say, if not only it's 5, it doesn't even look red, it makes me think of red, it's red in my mind's eye. But the lower synesthetes will say, it actually looks red, I can see red on the page, but I know it's black.
Hi, I was wondering if synesthesia could explain other phenomena, such as for people, let's say, that have very strong experiences, such as very strong religious experiences, or very religious experiences, or very strong fear experiences when there's nothing really out there to influence those types of experiences.
We've not seen anything to link, synesthesia with other types of associations. One thing I'll tell you though is there seems to be some link between mnemonic abilities, memories, and synesthesia. Luria's famous mnemonist claimed he uses his synesthetic abilities to remember a lot more detail than other people. And we have found one synesthete, so it's an N of 1 and we don't know for sure, one synesthete who had eidetic imagery. And we know this for sure because we showed him find Waldo for 2 seconds in front of him and removed it. Now you and I take a minute or half a minute to find Waldo. He inspected his internal image and found Waldo. And again, we did several trials and it seems to hold up. But what we don't know is it's just odd that it's coincidence that he also has eidetic imagery. And given that eidetic imagery itself is such a flaky phenomenon, I'm hesitant to claim that that's a valid finding, but we don't know.
At the end of the talk, you said if you ask the right questions about the right phenomena, you can make progress toward answering big questions. So for sort of young scientists, how do you find those questions? Or how do you find those phenomena? How do you identify the right patient, the right phenomenon? Is it luck? Is it intuition? Is it?
Well, all three, I guess. But I mean, in terms of general science itself, I mean, I found that having the right people to follow around, you know, people who are enthusiastic and passionate about what they're doing and have ideas all the time, that helps. But you're talking specifically about how to have ideas, and I don't know. It's a good question. I think it does rub off, you know, hanging around people like one of my teachers, Richard Gregory, and he was a very extraordinarily creative guy. And Irv Rock was another, not a teacher, but a close friend and associate. So I think that helps. Also, sorry, I'm going past your question. What was your actual question? Oh yeah, the other thing is, this is not everybody's cup of tea, but I tend to go after curious phenomena or odd phenomena, what Kuhn would call anomalies, right? And 90% of the time it's a wild goose chase, an anomaly, like Elvis sightings or telepathy or something like that. But sometimes an anomaly is a gold mine, like bacterial transformation or X-rays. Nobody could make any sense of it, but he said, look, there's something interesting going on. Just because we can't explain it doesn't mean the phenomenon doesn't exist. So those anomalies which are repeatedly repeated experimentally, but you can't fit into the big framework, those are the ones to pursue. Those ones which have not been repeated and you can't even confirm, like telepathy, avoid like the plague. Okay. So one strategy is to pursue anomalies. Synesthesia is an anomaly, phantom limb is an anomaly. You know, people knew about it, everybody knew about it, people thought it was a curiosity. And but by the way, you have to do 10 before you find one that's that's helpful. Yeah. 2 more questions, yeah.
Hi, I had a more general question going off your discussion of phantom limbs. I was wondering what you thought about the future of neuroplasticity as a treatment, especially with things like recovery from strokes or psychological disorder.
Well, I mean, there's a growing evidence, not from my lab, Pascal Leone, Baki Rita in the old days was an early pioneer. A lot of Mike Merzenich casts in animal physiology, and some of our work on phantom limbs, in mirrors, for example, it shows a tremendous amount of latent plasticity. But the question is, can you exploit it in other, this is an existence proof that it can happen. Can you exploit it for other types of neurological dysfunction? One can only try and see. But I'm much more optimistic now than I was when I was a medical student. But then the dogma was these are connections are fixed and you can't do anything about it, so on and so forth. So I'm giving you an equally general answer to a general question. So for example, like RSD, the pain that you get in 10% of stroke patients is excruciating. The fact that it can be removed with a mirror, you know, there's a patient database, about 50 patients. It's very striking. Nobody would have suspected that because it's a chronic, persistent pain. And if you can recover from stroke, then you wonder about Parkinson's disease. You wonder about various other neurological, progressive degenerative disorders where you get hemiparesis or paralysis, that sort of thing. But again, it's a very vague answer, admittedly. Yes. If someone is born who has a stroke at birth, yes, they can't move their arm, yes, in a position like this. Have you done any work with unlearning that paralysis? Yeah, well, I haven't, but with cerebral palsy in general, there are 1 or 2 groups using mirrors to try and do something and claiming modest success, but I don't know that literature. But if you go and Google cerebral palsy mirror visual feedback, there are a couple of papers, either or clinical trials maybe, which are advertised. I don't know how far they've got with it. I would suspect it should be even easier because the brain is so malleable when you're very young. But so if you have hemiparesis in cerebral palsy, maybe you could use the other hand to educate it and use a visual feedback to regain some of the function. I mean, you know, even in old clinical neurology, they used to tell us that if you're a Parkinson's patient, the guy is seated, he can't barely stand up and walk. He's frozen, stiff. And he's been like that for years. And then there's a fire alarm siren, and there's a fire alarm bell, and you say, fire, guy gets up and starts running. I mean, Jonathan, you must have heard this, right? So this shows that there's all kinds of latent circuits there, which, I mean, it's not some aimless running, it's actually running towards the door and away, right? So something is sitting there waiting to be unmasked or starting to function again. But nobody's tried it in Parkinson's. You know, it'd be very interesting. Yes. Yes, no, that's what I'm referring to. I mean, that's the cerebral palsy syndrome. And it could be that it helps them, but it hasn't been studied carefully. One more?
Sorry. Yeah, okay. You spoke at the beginning of your talk about a guy who, who thought his mother was an imposter visually, but when he heard her speak on the telephone, he could recognize her voice and knew who she was. So when she is in front of him, speaking to him, which one wins?
So just to repeat the question, here is a guy who says his mother is an imposter when he looks at her because of the postulated disconnection between amygdala and visual pathways and fusiform gyrus. When she speaks to him from the adjacent room on the phone, 10 minutes later, he says, "Hello, how are you, Mom?" And I said it's because the auditory pathway is intact. But if she comes in person and starts talking, why don't you the answer is she does not overcome the delusion. He still says it's an imposter. The reason is, again, because the visual system is, the brain is giving different weighting to different sources of information. And vision gets a extremely high weighting. So that overrides the fact that there is auditory stimulation of the amygdala. So there's an override. I think that's what's going on. So for example, if I came here tomorrow and I had laryngitis and I talked funny, you would say, "Dr. Ramachandran, do you have a cold or something?" Right? You're not going to say, "Hey, you look just like Dr. Ramachandran." Conversely, if somebody comes here who has my voice, you're not going to say, "Oh, you don't look like Dr. Ramachandran today," or something like that. So this is because, you know, vision has a high weight given assigned because of the logic of statistics, statistical logic of the external world. Yes, one more. I've never heard that. It's interesting. Usually the delusion is extraordinarily persistent and tenacious, and nothing you do can help the patient overcome. Yeah. Well, in clinical business or even in social sciences, there are always exceptions. You don't know how to explain them. And there are some schizophrenic patients who develop Capgras-like symptoms. So maybe he had schizophrenia, and maybe something else was going on in him as well, in addition to the Capgras delusion.
Well, the audience is seemingly unstoppable, but I think we're going to force them to come up to you and ask the questions.
Sure.
So let's one last time thank Dr. Ramachandran.